In this talk, we will discuss some MCQs related to the metric space, submetric space as a whole. So let us take the first question. So the first question is, we say that the space X has the property S. Okay, whenever for every epsilon positive, X has a cover containing connected subsets such that the diameter of each of them is less than epsilon. Okay, then which of the following statement is not true? So which of the following statements statement is not true? So here is the question, is that the property is that for every epsilon, X has a cover containing connected subsets such that the diameter of each of them is less than epsilon. Then which of the following is not true? A metric space X has the property S if X contains a dense subset with the property S. So here you can see that if you have a dense set, okay, if X has a dense set, then this property may be possible. Or you can see that the dense set, it means that actually the main thing is that we have not discussed the connected set. So the better way is I should leave this for a moment. So whenever you will study, and then you can check this one. So I go to the next exercise. So which of the following statement is not true? Okay, the first is S. Let S be a non-closed subset of R. Okay, then there exists a function with domain S such that F is not bounded. Okay, so you have like this. Suppose you have a function F. So and S which is not closed is a subset of R. Okay, to R. Okay, such that the F is not bounded. Okay, so you have to find, suppose an S is not closed. S is not closed. S is not closed. So if F is not closed, S is not closed, then there exists a function, okay, with domain S such that F is not bounded. Okay, so it means that we are saying that this statement, okay, so whether S is closed or S is open or S is anything, okay, the boundedness of the function does not depend on this one, because if there exists a function S such that S is not bounded, so if it is open, okay, for example, you can prove that whether this statement is true or not. So here there is no such result. We have studied that for if F is open set, then the map S from R to R is not bounded. Okay. The second thing is F and G are two uniformly continuous functions on a subset E of a metric space X. Then F composition G is a uniformly continuous function on E. Yeah, this statement is true because we have seen that the composition of two uniformly continuous function is continuous. If A and B are two non-empty subsets of R such that A is less than or equal to B for all A is in A and B is in B, then the supremum of A is less than or equal to infimum of B. Okay, and if a function f is uniformly continuous on finite number of closed intervals, then f is uniformly continuous on the union of them. So this we have to verify, but you can say that A is not a correct statement. Okay, now let's take here is another example exercise. So for another MCQ, we can have here is you take S is a subset of R2, where lies between this and that. Means what? It means that you have R2, so you can draw R2. So X lies between -1, so this is your -1 and this is your 1, and here you have 1 and here you have -1. So you have this is your S. Okay, so this is your S, and then as T is, you can remove this one. So let me remove this one. So you remove this portion, and so rest of the portion is this. Without this is your capital T. The set contained by removing the origin from this. Consider the following statements. So again, here is the set is connected. Yes, this set is connected because R2 minus 0 is connected, so this set is connected. You can it is basically path connected, so it is connected. Now whether it is your compact set or not, but this set is not compact. Okay, this set is not compact because what you are doing, you are taking this set, if every sequence has a convergent subsequence. So you will find a subsequence which is converging to 0, 0. And then you can say that it is not compact and it is also not closed. But it is bounded. Okay, it is bounded. Okay, so what are the things that you can see that A is connected, it is true, and D is bounded, so D is bounded, so answer is D. Okay, so the answer is D, A and D. So this is A. It means that this set is connected as well as it is bounded, but this set is not compact and this set is also not closed. Okay, so this way you see here is, and let's take the next MCQ. So we can have some other MCQs. Here is we have a set consisting this is x plus 1 is the circle with the center at -1, 0, radius 1. Okay, so you have a disk and you take the union with all the points satisfying y is equal to x sine 1 over x. Then x is connected. Then you will see that x is connected, but this is not compact. Okay, because this set may not be compact. Okay, and also this set may not be closed, so it is not closed, and this set is also not bounded, so the whole set is not bounded, and so it can be compact but no other choice. Okay, so these are the some miscellaneous exercises or miscellaneous MCQs. Now we will see some results related to some MCQs related to the fixed point theory. Okay, so before going to the fixed point theory, let me recall the definition of a fixed point. So here is again I am recalling. So suppose you have a map T from a set X to itself. Keep in mind, when we talk about the fixed point, we always consider this map from a set X to itself. Okay, not the map from x to y. So first is the map x from x to itself, then a point x. This is called a fixed point of t, if what is happening, t of x is equal to x. And then we have seen that a map can have a unique fixed point, can have more than one fixed point, and may not can have infinite many fixed point, or may not have any fixed point. Okay, and then we have mentioned that about the contraction map. So here the important thing is that suppose you have a map T from xd. Okay, xd is a metric to xd to itself. Then this map is called this called is ellipsis continuous if d of tx ty is less than or equal to, I can write here is alpha times d of xy for all alpha y, sorry, for all xy for all xy in x. So it means that here is if there exists alpha greater than 0. Okay, so if this alpha lies, so if this condition is holds good for alpha is greater than or equal to 0, then T is called ellipsis continuous. If alpha lies between 0 and 1, okay, then this map T is called contraction. Then the map T is called contraction. If alpha is equal to 1, then it is called non-expansive. Okay, and if we remove this one, if we remove this all, this if it is this condition holds good, okay, so we can take this is less than, then T is called contractive. Okay, so this is what the definition, and we proved that a contraction mapping. So we have proved that that is called Banach contraction theorem, which was a contraction mapping defined on a complete metric space to itself has a unique fixed point. Okay, this we have already proved. The second, we have proved that if T is not a contraction map, but it is a contractive map. Okay, in that case, we will have to add something on the space. That is to say that instead of taking x is complete, we will have to take it is a compact. So if T is a contractive map defined on a compact metric space to itself, then it would have a fixed point. Okay, so that is these were the two important results which we proved in the chapter of fixed point results. Now with this, let us take some MCQs. So first, let X is equal to R be a metric space with the usual metric, and T is a mapping from X to itself defined by Tx is equal to x upon a plus b, where a and b are real numbers. Okay, which of the following is true? T is a contraction if a is greater than 0. T is contraction if a is greater than 1. T is a contraction if b is greater than 0. T is a contraction if B is greater than 1. Now look here is, the important thing is that there is one thing, either you use the definition or you use the Banach contraction results. So there are two ways to get the answer of this question. Number one, what you can do, you can prove that this is a contraction. Contraction means you have to T mod of T of x minus T of y. There exists alpha such that this is holds good. Okay, alpha lies between 0 1 such that this is true. So you have to prove this one. Then you can say that it is a contraction. So let us start by you doing this one. Okay, so let us start. So then what you will get? You will get on the left hand side mod of x upon a plus b minus y upon a minus b. Okay, so b is cancelled out and you can take 1 over a alpha, so x upon y. Okay, so it means that this mod of Tx minus Ty is less than or equal to basically is equal to 1 over a mod of x minus y. Okay, so it means that this is less than some alpha mod of x minus y, where alpha lies between 0 and 1. So it means that you can take this is what? This is less than 1 because we have to take the alpha. Okay, so this is less than. So here is we have to prove that this is less than or equal to. Okay, so this is less than or equal to. So we can take 1 over alpha is equal to s. So this is true only when a is greater than 1. If a is greater than 1, then this term will lie in the open interval 0 1, and then we can choose this is equal to alpha. So the answer is your B. The second part is to prove, to check whether is a okay. So this way you can prove. Now you know that if this is a contraction, okay, and now the next question is if this, now we have proved that suppose a is greater than 1. So if a is greater than 1 and T is your complete x is your complete metric space with the usual metric, then T would have a fixed point by the Banach contraction theorem. So by Banach contraction theorem, if x is a metric space with the usual metric, okay, and it is because x is equal to r, so, and r is complete with respect to the usual metric, and we have shown that T x is equal to x upon a plus b, where a is greater than 1 is a contraction map on x. Then this T map should have a unique fixed point. Now the question is, what is the unique fixed point of this? How will you find it? What would be the fixed point of T? So it is very simple. You can simplify. You can take, suppose we had fixed point T of x is equal to x. So this you can write as x upon a plus b. So you take from here you can take x minus 1 upon ax is equal to b. So you take x is common and then 1 minus 1 over a is equal to b. and x is equal to, so you can write a minus 1 is equal to b, and x is equal to b into a upon a minus 1. So this is the fixed point. You will get this way. Okay. So this is the question. Of course, you have to fix. So for each fixed a and b, you will get a fixed point of t. And then the next question is, let x is equal to R2 be a metric space with the usual metric, and T is a map from x cross x, okay, defined by Txy is equal to x upon a plus b, x upon c plus b. Okay, which of the following is true? Okay, then again you have to check which of the following is true. Now, T is contraction if A and C is greater than 0, A and C greater than 1, A and B greater than 0, B and C is greater than 0. Just we have seen that if it is a single, because here just we are taking is a function T is a function from R2 to R. So we have two components, and only the thing is that they are same. So if we have seen that for the single component, if A is greater than 1, then this is a contraction map. Similarly, if C is greater than 1, then here you have a contraction. So A and C should be greater than 1, then T would be a contraction map. And now the question is again, what would be the fixed point of T? Because R2 with the usual metric space is a complete metric space, and T is contraction with A and C is greater than 1. So find out the fixed point of T. Now we take next exercise. We say that if X is a metric space and T is a mapping, self-mapping on X, and SRX is an open sphere with radius R greater than 0, enough large, centered on X, then the image of open ball under T is a subset of SRTX. Okay, SRTX. Do you remember that the image of open set? So we have proved that this one is, we have proved that here, you can look here. In the contraction map, if you have this is your ball with center at X and radius R, okay, enough large, and T is a map from this here to here. And now what you are getting, and if this S lambda T of X, this is the open ball with center at Tx and radius delta, then this whole ball is going to this smaller, was contained the image of this, okay, the image of this ball contained in this ball. Okay, it means that this is the image of this ball. So if T is a contraction, then the image of this ball, okay, contained in the open sphere with center at Tx and radius epsilon.